Hello everyone, and welcome to SNIA's Ethernet Storage Forum and everything you wanted to know about storage, but we're too proud to ask. Today we're going to be treated to Part Rosé, which is a webinar specifically focusing on Iscuzzy. And today we're going to have a number of experts in the field that are going to be able to provide you with some of this information. My name is Jay Metz, and I'm going to be your host for today. And today I'm joined by Loy Evans, Technical Solutions Architect from Cisco, Rob Davis, VP of Software Architecture at Mellanox, and Alex McDonald, a Standards Technologist at NetApp. And today these gentlemen have volunteered to be your gurus for all things Iscuzzy storage. Now, in case you're new to SNIA, we are an industry association that represents 160 unique member companies. We have over 3,500 active contributing members that reach a community of over 50,000 IT end users and storage professionals worldwide. Now, before we get started on today's webinar, a little bit of administrivia. First, if you find yourself having problems with the audio cutting out, which can sometimes happen, we found that this might be an issue with various browser caches, and emptying the cache or reloading the browser often helps. Second, the information contained in this presentation is copyright by SNIA, and any member company and individual members may use this material in presentations and literature, as long as the slides aren't modified and that SNIA is acknowledged as the source. Of course, even though we do the best to be as accurate as possible, you are encouraged to use this wisdom and scintillating brilliance at your own risk. And one final bit of information, please feel free to use the question button at the top of the screen to ask anything you'd like during the course of this presentation. We will do our best to answer them in the time allotted, but also don't forget to rate this presentation. Constructive comments are most appreciated. If you have any concepts or topics that you would like to see in the future, that's the best place to put them. And last but not least, this presentation will be available along with a blog that addresses all the questions that arise during the course of the webinar at a URL that we've posted in the end. So, now that we got the housekeeping out of the way, let's talk a bit about what we're going to be talking about. This is your first Too Proud to Ask webinar. Welcome. You may be wondering why we're doing something like this. Well, as technology improves, we're seeing an awful lot of cross-pollination between different areas. As a result, IT professionals are being asked to pretend they know everything about all IT. And so we often find ourselves in sticky situations, something like, hey, I've been having conversations with people about storage and pretending to know what I'm talking about, but I'm tired of having to fake it till I make it. So don't worry, your secret is safe with us. This session is going to focus entirely upon Iscuzzy. As you can see, these all fall into the categories of host and network. We're not going to be focusing too much on the target side here, even though obviously Iscuzzy targets are a very important part. We do recommend that you take a look at our first Too Proud to Ask webinar, Part Chartreuse, that goes over many necessary terms for both hosts and storage. In addition, we've also recently created a webinar on the evolution of Iscuzzy, where we take the conversation to the next, more advanced level. Links to both of these will be shown at the end of this presentation, so it's a little bit of encouragement for you to stick around. For now, though, with all of that out of the way, let's get started on Part Rosé. We'll be starting with a brief overview of Iscuzzy and how it works. And then we'll be talking about the two main ways that you can deploy Iscuzzy with host-based software and hardware-based offload. Now, you'll need to remember that we're not recommending best practices. The purpose of this webinar is to help you understand what these things are and how they work. The decision on what to use is going to depend entirely upon you. So, with that, I'm going to pass this over to Alex McDonald, who will get us started with a brief Iscuzzy overview. Alex?
Thank you, Jay, and good morning, everyone, or good afternoon, good evening, good wherever you are. I just wanted to do a brief overview because I think it's good to try and position these things before we start on the body of the material. So today, as the old guy, I drew the short straw, and I get to do the history of the thing. So here's a brief Iscuzzy overview for you, and it is brief and pretty high level, so bear with us. This is think back in terms of scuzzy, first of all. Let's forget the I bit and talk about the small computer system interface. Perhaps you're old enough to remember it, but it was originally designed for communication with a variety of devices. Things like disks, yes, but also tapes, scanners, toasters, various other bits of technology, fish fryers, various bits of technology that could be addressed by this small computer system interface. The small bit's kind of gone by the wayside now, and obviously we've seen an awful lot of scale over the intervening 20-odd years. And it's now, I'd say, almost exclusively, although I'd probably get shot down by tape people for this, almost exclusively for disk-like devices. So the SCSI interface is pretty well understood, pretty well known. It's been around a long time, and people are pretty comfortable with it. What Fibre Channel did for us, why am I mentioning Fibre Channel here? Because what Fibre Channel did, and it's something that we see increasingly in the IT industry, it's a really good thing to separate out various layers of the components that you're trying to deal with and manage. And what Fibre Channel did was drive the separation of the device, the thing that we're talking to, versus the transport, what we talk over it to. And commands for devices versus how the commands are transmitted was something that Fibre Channel really introduced to the SCSI world. So the iSCSI approach is, let's use the internet for this, and use TCP/IP as the basis for the transport. Now that actually makes this quite interesting because it's the only mainstream SCSI transport that doesn't do any hardware definition, because TCP/IP doesn't tell you on what it's carried. It's really a pretty agnostic protocol. You can travel on quite a lot of different hardware, and we'll talk about that in a second. And what iSCSI does is define block storage over a standard TCP/IP network. That's a little history. So here's what iSCSI looks like. It's basically an encapsulation, standard TCP/IP encapsulation of the SCSI command. So we've got the iSCSI data in that really dreadfully sludgy green color in the middle. That's the protocol data unit, the piece of information that we're delivering between the iSCSI stacks on both sides. And I'll talk about that in a second. And then the outer parts of the onion are the layers that are used to transmit and carry it across the technology. So in other words, we've got TCP headers, and then we've got IP headers that allow us to route and make sure the packets can find their way through the network. And then if we're carrying it over Ethernet, we've got the whole thing wrapped up in an Ethernet header. So effectively, iSCSI is just basically the encapsulation of SCSI commands in some transport protocol, TCP/IP in this case. So a pretty simple concept, really, if you think about it. I mean, TCP/IP is pretty ubiquitous. In terms of how it works, basically this is a request response protocol. It's a fairly straightforward connection-based protocol. There can't be any response, as it says here, until there's been a request. So an iSCSI or SCSI requires a request to be able to respond to it. And there are two types of iSCSI or SCSI piece at each end. One is the initiator, that's where the requests start out, and the target, where the requests are serviced and the responses are created. Now, I'll discuss that in a little bit when we talk about how the average iSCSI session is set up over the internet. So the SCSI initiators are usually hosts, computer equipment, things like servers, arrays, workstations. But hosts can also be targets. There's nothing explicitly saying that an iSCSI an iSCSI initiator has to be a host. It can be pretty much anything that you can start an iSCSI conversation. The other thing to recognize is that iSCSI initiators, they can actually maintain multiple parallel connections to multiple targets. We'll talk a little bit about that in a second as we just go through the overall concepts. So iSCSI, what's the iSCSI bit of this? The iSCSI is the client-server piece that provides the interface between the various components over the network, and effectively any type of SCSI device can be accessed over iSCSI. Block storage is the most typical, and in fact it's the only type supported on a Windows server. But the important thing here is that we can run TCP/IP over anything that you care to mention. We can run it over Ethernet, we can run it over InfiniBand, and we could probably run it over two pieces of damp string, because I'm sure there's somebody somewhere who's actually generated a TCP IP stack that runs over stuff that we've never even heard of. So basically, anything that we can carry IP traffic on, we can carry scuzzy traffic as well. And if you're desperately interested in the protocol specs, you can see there, I've just noted down some of the protocol specs that are used in defining Iscuzzy. So, last but not least, let's talk a little about how Iscuzzy does its work. So this diagram on the right-hand side, meant to look like a whiteboard, and it comes in basically several parts. So I'll describe each part in turn. So first of all, we've got in this case, a box, an ESX box, that contains an Iscuzzy initiator, and that's marked number 1. You can see the 1 underneath the Iscuzzy initiator piece. And on the right-hand side, we've got another box, an array of some description, a SAN, let's say, that contains an Iscuzzy target. And on that side, we've got various bits of technology, including disks that we're going to provide data from. So the process by which Iscuzzy sets up these connections, there are various names that parts of Iscuzzy have. I'm not going to go into too much detail, but basically there is one port that we use to gain access from initiator to array. So the initiator to target. So the initiator, excuse me, I'm stumbling over my words there. The initiator knows how to contact the target and does so over a known port. And it will do through that network interface card. You can see the 2 network interface cards there, and down through the connection through some form of switch. And once the initiator and target have spoken to each other, then we can set up the sessions. And so you'll actually see in number 5, we'll actually set up a session, an Iscuzzy connection. And that results in the ability to multipath. So we've got a multipath ability. So the initiator has talked to the target down a known port. The target and the initiator understand, based on names, how to communicate with each other. They understand the paths over which they can communicate, and then they set up those sessions over the path, and you end up with an Iscuzzy connection. So it's a connection protocol, it's stateful, and basically the initiator starts the process, and the target is the one that provides the data on request from the Iscuzzy initiator. So what we're not going to do today, because this is meant to be an overview, this is meant to give you some understanding of what the technology is about. We're not going to cover some of the more advanced topics, but there are plenty of other SMEA resources. In fact, there's a Iscuzzy overview that I recommend you go and look for on the website. There's also iSER that we discussed, which is the extensions for RDMA, which is remote direct memory access. So that's a protocol that allows you to do remote memory to memory without involving the servers on both sides and then CPU overhead. You can talk memory to memory via the network interface cards. There's also single multi-route I/O virtualization, which is a PCIe bus specification for virtualization, because virtualization changes some of what we're going to talk about today. And there's RoCE and IWAP and perhaps other technologies that you've also heard of. But there's a huge amount of this advanced material. What this session is meant to do is simply bring you an overview of Iscuzzy, and so that you will have an introduction to the topic. If you want to find out about these other pieces, use the site keyword on Google search, site:/SNEA.org will limit any search you do just to the SNEA site, and then you can add in, for instance, labels like Iscuzzy, RDMA, and you'll get back all the presentations and the white papers and documentation that SNEA produces on Iscuzzy and RDMA, and the same is true for SRILV, RoCE, IWAP, etc., etc. So with that brief introduction, thank you for listening to me. I'm going to hand you over now to Rob Davis, who's going to talk about host-based Iscuzzy. Rob.
Thank you, Alex. Hello, everybody. Following the tradition of our Everything You Wanted to Know About Storage series, on the first slide of my section, I'm going to show a general definition, and then I'll go into details and break it down in the rest of the presentation. So Basically, what we have with host-based iSCSI is just software in the operating system using an Ethernet port to connect to an iSCSI SAN. And basically from the initiator side, this is the most common approach to implementation of iSCSI from the initiator side, if you remember Alex's definitions. So let's get into some more details. Alex did a fantastic job of explaining the various pieces of iSCSI and how it works. What I'm going to do is, with this diagram, I'm showing the total parts of the iSCSI stack that we're going to break down, and I'm going to focus on the parts that can be either host CPU based or offloaded. This can start as high as the iSCSI command set in the stack, and it can go all the way through the IP layers, and even be just parts of these layers. So there's partial offloads that we'll talk about as well. And later in the next section, we're going to deep dive on the actual offload piece as well. So with host-based iSCSI, sometimes called onload because you're onloading the task to the CPU, most of this stack is done in software running on the CPU. I say most because all standard NICs today have some TCP offloads, but not the entire stack, but parts that are easily put into hardware that provide the most payback in saving CPU cycles. An example of this would be like TCP Checksum. That's an example of a partial offload. And this is now found on almost all NICs today. Now, this was not true 15 years ago when all of this, when iSCSI started, but over time, you know, these offloads have come to market. I should have said partial offloads have come to market. If we look at offload, in offload, a much bigger portion, often all of the iSCSI stack is handled by the NIC. How much of the stack and how it is done varies by vendor, and Loy is going to explain the different approaches in detail coming up in the next section here. But at a high level, some vendors implement the solution in firmware running on the RISC processor on the NIC, and others implement this in ASIC gates, or it can be a combination as well. And here you can see the different approaches side by side. Both have been in the market for, you know, probably 15 years and are implemented widely and are great solutions for Ethernet-based SANs. And it's also very important to understand that they can be mixed within the SAN. Some nodes can be host-based or onload, and some can be offload. The two approaches are completely interoperable. So looking at the highlights of host-based, first of all, I know nothing can be free, so how can I say this? But if you think about it, every CPU or every server has a CPU, an operating system, an Ethernet port of some kind, and every OS has an iSCSI stack. So unless you are using every available CPU cycle on your server, it's basically free to use host-based iSCSI. Because host-based iSCSI is part of the operating system, it is also extremely widely distributed and tested, and quickly, so problems are found and quickly repaired. It's software, so it doesn't require an ASIC respin or a card replacement, just a recompile and an update at the next release cycle. Also, other updates needed outside of iSCSI, for example, in the scuzzy stack or TCP or IP stacks, they all come automatically. and innovations in other stacks. For example, recently there have been updates to the scuzzy stack to add multi-queuing. Those come automatically. So innovation comes automatically. And finally, there's no vendor lock-in. Any NIC can run host-based iSCSI, but the interface to offload cards is often vendor-specific, and especially on the target side, this can lead to vendor lock-in. The obvious downside to host-based iSCSI is that it's host-based. It uses the host CPU to run the iSCSI protocol stack. Like I said earlier, there's certain offloads that even, general purpose NICs use, like the TCP Checksum, and there's also something called large segment offload, and those are standard in most NICs, and so this helps. But CPU resources are definitely consumed by the host-based iSCSI. How much depends on a lot of factors. First of all, the CPU technology, obviously the speed of the Ethernet port, the size of the message blocks, the frequency of the traffic, meaning how constant it is. Here's a couple examples of testing the CPU cycles of iSCSI with different Ethernet speeds. This is using an Intel CPU that was released in the market in 2014. So you can see with 100 gig Ethernet, and this is using a pretty big block size, MTU of 1,500 blocks. You can see the machine's capabilities. We were seeing in this testing 25% of the CPU was used to run a 100 gig Ethernet link, iSCSI link, and 10% for 25 gigabit Ethernet. So here's what you can expect to see from other technologies going forward. Luckily, the speeds of the Ethernet ports have increased as the CPU technology has continued to improve. And so you're going to see over these next two slides how that performance of iSCSI has kept pace. So this slide is showing a 2010 CPU technology and a 10 gig Ethernet port and a Windows-based Windows operating system running an iSCSI software stack. Now, at this time, it was sort of before the time of SSDs, so it took a lot of hard drive targets in order to produce the load needed. But 1 million IOPS in a Windows environment in 2010 was not bad. Pretty good performance, actually. Jump ahead to 2016. So this is last year, a CPU released last year. And we're seeing, in those 6 years, we were able to double the performance, so 2 million IOPS. And also, this is a perfect example of ability to take care of or to take advantage of innovation with the host-based iSCSI, because here is a new technology called SPDK. And with the SPDK technology added on the same machine, they were able to improve. It's able to improve the performance to over 3 million IOPS. In this particular configuration, those 3.3 actually million IOPS we're using 38% of the CPU. So as I was saying earlier, that's the trade-off. This is a pretty high number because the way SPDK technology works, it basically dedicates cores to the I/O to eliminate the interrupt latency, and that's how they get the faster IOPS. But that dedication means that those cores that are dedicated are 100% used for the I/O, which drives up the CPU utilization. So here we can see how host-based iSCSI is able to take advantage of not only the new storage technologies like SPDK that I showed before, but also leverage the cost curve and power reduction of the CPUs over time. So what this means basically is that the increase in performance over the years that we showed have not increased the overall cost of the solution. And with that, I'm going to now turn it over to Loy, who is going to give you a more detailed description of Iscuzzy Offload.
All right, thank you, Rob. Appreciate it. So as mentioned, we're kind of basically just kind of doing a baseline on all of the different possible things that can go into your consideration of how to deploy Iscuzzy. And in this particular section, what we'll do is talk a little bit about the things that can be done in order to offload some of the TCP processing. So what is TCP Offload? TCP Offload is basically, at least the TCP Offload Engine, is basically a hardware function that is used on some network interface cards to offload the processing of the portion of or the entire TCP/IP stack to the network controller. And by doing this, by moving some or all of that processing to dedicated hardware, that can reduce the load on the main system CPU for other application type tasks. The truth is this is almost every single thing that we talk about in here is going to be your mileage may vary, and there is not really any one specific rule that we can tell you if you do this you will save that. But we're going to basically go through and just kind of talk about what the possibilities are that you can use within your Iscuzzy deployments. So what's the reason why TCP Offload actually even came about? TCP was developed a long time ago when connectivity was really delivered on unreliable links, and TCP was designed at that time to manage those connections and manage delivery across those connections to compensate for those unreliability in those links. So what TCP management actually does is it takes up some CPU on the host to manage things such as the actual connection setup and establishment, the ongoing acknowledgement of packets and frames that go back and forth, calculating the TCP windowing so that you basically are kind of sliding the window open or close depending on how much loss there is in a network and how much it thinks that it can guarantee delivery of over a certain amount of time. Also doing things like checksums. Since we're kind of chopping up the original data, we want to make sure that when it gets there, it hasn't been tampered with or hasn't had any kind of corruption along the path. And the checksum basically does a verification that what was sent is actually what was received. And that's something that, as we get down in this list, we get a little bit higher into the amount of CPU that gets taken up. And then actually doing the congestion management and all of the window adjustments that, again, not just the calculation, but doing the adjustments on the fly. Those are the kind of things that do take up a bit of the CPU that the server has. So if you kind of look at just in general, it's a very hard thing for us to go in and say explicitly, if you have this much Iscuzzy traffic, it's going to cause this much or cost this much overhead. But essentially, if you are doing a pure software onload, as Rob had mentioned, essentially the Iscuzzy stack puts the burden of the extra TCP overhead on the OS and CPU for the storage, right? So if you were to do a direct comparison to some other, like maybe just a local scuzzy, you're basically just going to be using the I/O interrupts. In this particular case, you're using the I/O interrupts as well as using TCP overhead for communications. And this is going to be processed by the CPU, and the overhead that is going to be processed depends very much on the type of workload and also fairly heavily the percentage of Iscuzzy data that gets transmitted in relation to the application CPU load. Now, just to kind of give you an example, if you had a server that had a 10 gig NIC that you were using for exclusively Iscuzzy and a 1 gig NIC for exclusively application traffic, if each of those interfaces were to run at 100%, it is possible that you could have Iscuzzy overhead that is 10 times what the application traffic overhead would be under TCP. Now, again, this is not a hard and fast rule. This is just kind of a possible way that you can look at this. Now, with TCP Offload, essentially there is specially baked hardware that runs on the Ethernet NIC. There are certain cards that will have this capability. As Rob mentioned, there are also certain pieces, and we'll talk a little bit about the types of offloads that can be done. Some of these can be done on a generic NIC. Now, that's not necessarily on specialized hardware, so once again, your mileage is going to vary on how much savings you can get. So if we have that tow card on the NIC, essentially at that point you can decide, how do I want to offload this, and then the NIC basically handles some percentage of the TCP overhead depending on what you choose to offload, depends on the type of workloads on your server, and the traffic patterns that are actually being processed at that time. But you can, at that point, in almost all cases, see some change in the amount of TCP overhead that the CPU, IO overhead that the CPU has to process with the presence of a tow card. So an example of kind of pushing the work down to the network, a full stack offload. Essentially, what happens with this is that it goes from the NIC being the boundary of the L2, L1 communications to actually taking the TCP and IP stack management and pushing 100% of that down to the NIC. Now, this is something that will be in some case dependent on the type of card that you have and the support of the operating system for that. But as Rob mentioned, there are a lot of possibilities for doing this, but just double check to make sure that the card that you're looking at and the operating system that you have, there's support for those. So if you choose to not do 100% offload, one of the other possible ways of doing this is basically doing what's called TCP Chimney Offload. So essentially what this is that the OS still manages the connection establishment and security and build up and tear down of the actual communication. But once it gets that done, it basically uses its driver to the NIC to pass the state down to the NIC, and the NIC handles all of the transmit and receive. So basically it does all of the window management, all of the checksums, and all of those types of things. So this is kind of a hybrid type of approach to doing offload. In this particular case with TCP Checksum Offloading, it's somewhat similar to the chimney, but instead of instead of the NIC handling all of the communications, basically all it does is offload the checksum calculation verification. So it's basically kind of an inline job within the TCP flows. Now again, this one right here, this particular type of offload is something that is available obviously on cards with tow, but in some cases, and I'm not going to say all of them have it, but in some cases you'll see some checksum offload capabilities on just some of the generic NICs that are available in the market. Now, one of the things when you're talking about specifically large data sets, there is another way that you can do this, which essentially is offloading of the buffer capabilities from the operating system down to the NIC. So there's a thing called large segment offload. There's also another name for it called TCP Segmentation Offload. But basically what this does is the operating system opens up an I/O channel and it, excuse me, I'm sorry, let me reset that. The operating system normally has to manage large segment breakdown into the smaller chunks that would be sent out of the NIC in the TCP/IP window packet sizes. So without that, the CPU has to do the calculation of where to do the segmentation, and actually has to use CPU to break down those chunks into smaller components, and then it passes those smaller components down to the NIC. But with this type of offload, essentially the operating system will open up an I/O interrupt and send the large data segment down to the NIC. The NIC will actually do the breakdown of that into the smaller chunks and the TCP/IP packets, and there's very little overhead on the CPU for that. And this specifically is used for increasing outbound throughput in a TCP or Iscuzzy type of environment. So if you take that scenario that we just talked about with large segment offload, there's a thing called large receive offload, which is essentially the same thing in reverse. So without this, essentially you have a bunch of small TCP packets that normally are reassembled into a large segment on the host in the CPU. So basically the whole host has to hold the TCP connection open during the transfer, take in all of those packets and use its host RAM for buffering, and then it will utilize the host CPU to reassemble that into the large data segment. with this, essentially the NIC takes in all the TCP packets and aggregates those, and then it basically sends just one large segment up to the operating system with a single interrupt. So what this is built for is, again, just the opposite of the large segment, which it increases the inbound throughput of the iSCSI traffic. So I will, at this point, in summary, the TCP Offload Engine is essentially a chip on a basically certain NIC that allows offloading of the TCP stack functions from the operating system to the hardware. You can do full or partial stack offload, and basically these things are usually configured in the BIOS, and whether it's an actual PCI card or it's some sort of a board that's actually on the motherboard or something of that nature. But usually it has configurable options that are reachable through BIOS. And one thing that's interesting about the tow cards that is a little bit of a differentiator between an Ethernet NIC with tow or a specific iSCSI purpose-built card is that a tow card can be used for offload of TCP for iSCSI and other TCP functions. Whereas if you're looking at an iSCSI HPA or NIC, it is actually a specialized card made just for iSCSI offload, and it may or may not be able to do offload of any iSCSI or non-iSCSI TCP workloads. So with that, I will now hand it off to Dr. Jay Metz and let him basically wrap us up.
Great, thanks, Lloyd. We've got a couple of questions that have come in, and I think that given we just had the conversation about the onload, it looks like we've got your mileage may vary question that came in. Does high-density virtualized workload represent something better served with a full or a partial offload solution?
I guess the question would actually come down to, what are we talking about as far as high-density virtualized workload, right? Is that a high-density, VDI workload, or is that a high-density of, virtual machines that are doing file services, right? It's really going to kind of depend on what the best, what the type of traffic flows and workloads are. If you've got something that is extremely chatty, like a lot of small files and small data segments that are being sent, you may have a fairly high amount of TCP overhead per data byte sent. So it's going to somewhat depend on what the workload is, what the mix is. Unfortunately, a high-density virtualized workload, I'm not quite sure I can really give you a very specific answer for what the right the right way to go is with that. Okay.
And then we got one for Rob, too, actually. On one of your slides, Rob, you talked about a host-based iSCSI solution using an SPDK target. Can you take a brief moment and explain what an SPDK target is?
Sure. So SPDK is the storage version of DPDK, and it's a technology that has come out pretty recently in the last couple of years to try to reduce increase the performance by reducing the latency of all the different software layers in a server or an application. And so what it does is it dedicates cores to the I/O, and by dedicating cores to the I/O, it eliminates the interrupt latency that happens between the adapter and the software in the operating system for the I/O. And that interrupt occurs when data is either coming in or has been transmitted, and it's a kind of a response telling the operating system that it has been transmitted. Instead of waiting for that interrupt latency, which can be typically about 10 microseconds, instead a core or multiple cores are dedicated to pulling the I/O adapter. So they're looking at the I/O adapter's completion queues, or they're watching the transmission, and instead of having to wait for the adapter to say through an interrupt that it's completed its task, it knows right away because you've got a Pentium core or whatever watching it every few nanoseconds. So The SPDK version is the storage version of the DBDK that implements the improvements in the performance of a storage target by following that methodology.
Sounds good. Here's an interesting question, and we may have to put this onto the Q&A. It may actually require more time than we have to go into at this point. But I'll throw it open in case anybody actually wants to address it. Is Iscuzzy ever going to be able to work with object storage? Anyone want to take that, or shall we try to put that into a separate pod?
What kind of storage, Jay?
Object.
Well, Iscuzzy is underneath. Well, you know, so if you think of typical object storage implementations, they're on top of block somewhere, and sometimes on top of file. And so at the bottom layer, you can have any block interface, you know, whether it's just a DAS scuzzy SAS interface or it's a remote iSCSI interface.
Right, and I think that we're probably going to have to think about doing another storage pod, Too Proud to Ask, on the series for what the differences are between different storage types, because I think that that's a very good question, but it opens up a Pandora's box of explanation. So whoever asked that, thank you very much for asking that. With that, I think we can probably sum up everything. And let's take a look at what we've done today. Now, Iscuzzy has been around for a while and provides the data center storage with a number of deployment opportunities. It's a TCP IP encapsulation standard for SCSI block storage, as Rob just pointed out, and separates out the storage protocol from the hardware. Because of that flexibility, it's possible to choose a couple of different ways to deploy the protocol. With advances in storage and CPUs, host-based software allows you to use Iscuzzy using a server standard Ethernet NIC. Or, depending upon the traffic characteristics in your data center environment, there's an opportunity to use offloading, which uses hardware on specialized NICs to reduce the load on CPUs. Now, like everything else in the data centers, there are advantages and disadvantages to both approaches. But in either case, Iscuzzy itself provides reliable and flexible block storage over existing Ethernet infrastructures. Now, as promised, here are the links to the additional webinars that we've done for the Too Proud to Ask series, as well as a deeper dive of advances in Iscuzzy. Now, I'm going to move off for just a second. Don't panic. I'm going to move to the final slide and return back to this one. So just bear with me, and we can get to the links in longer detail. But before you go, please do not forget to rate this webcast and provide us with feedback. If you've got any questions or wish to examine other topics, please let us know. We're looking for constructive criticism so that we can always improve on the next webinars. We'll be providing a full Q&A to this webcast, as well as the slides from this presentation on our SNIA ESF blog. And we have many more webinars on the way, and we'll be announcing them on our Twitter account. Yes, in case you're wondering, this is a shameless plug for following us on Twitter. So with that, I'm going to return the slides to the link page. And on behalf of Alex, Rob, and Loy, I'd like to thank you for taking the time out of your busy schedules to spend with us on Iscuzzy today. We're looking forward to sharing more storage information with you in the future. Thanks again, and have a fantastic day.
Thank you all.